Hello and welcome to this second video where we will discuss about radiometry and light collection. We will specifically speak about flux, intensity, radiance, irradiance and more. Enjoy! In the previous video we spoke about how to define the aperture and the field of view of an instrument. It is possible to do so thanks to two main ways which are called the marginal ray and the chief ray. The marginal ray goes through the edges of the aperture stop. It limits the quantity of light inside the system. The chief ray goes through the center of the aperture stop. It limits what the instrument can see. Field of view and aperture can be studied in another way with radiometry. The idea is to understand what quantity of light is collected and from what source. The study of how light is transferred from one object to an aperture is radiometry. Here, the aperture collects light emitted here by an extended source. The apparent surface of the object which emits light represents the field of view of the instrument. So let's introduce now some useful definition for the next part of the video. What is an angle first? Plane angle is the angle formed by two radii of a circle. It is defined as the ratio of the arc length to the circle radius, and its unit is the radian, while a solid angle is the ratio between a subtended area on the sphere and the square of the sphere radius. This unit is the steradian. To summarize, we consider solid angles subtended by aperture from sources or by sources from aperture. Here is the same formula as previously, used to describe the solid angle subtended by an aperture from a source. The aperture is, in that case, aligned with the source. In the case where the aperture is not aligned with it, an obliquity appears. It means that less flux is captured by the aperture from the source, which makes sense. In the case of a source with a central symmetry, for instance a Gaussian beam, the flux coming inside the pupil is not identical in each zone. Hence, it is necessary to take this fact into account by looking at each part of the pupil separately, using an infinitesimal ring solid angle. Finally, one can also define a solid angle by a cone subtended by the aperture with an angle theta. How does light transfer from one aperture to another or from one source to an aperture? When considering the transfer of light, it is necessary to consider a pencil of light coming from an extended source to an aperture. This quantity is called the geometrical extent, or étendue. It is possible to define this pencil of light with different ways. First, we can consider two apertures at a finite distance with an obliquity. Their area is dAs and dAr with an obliquity θs and θr, and they are separated by a distance d. This étendue is given by the formula. Another way to define a geometrical extent is to consider an emitting aperture and the solid angle dΩs subtended by the receiving aperture seen from the emitting aperture. Finally, another way is to define a solid angle dΩr subtended by the emitting aperture as seen from the receiving aperture. It is important to note that this transfer of flux works from surface to surface through a whole optical system, lens after lens. The étendue is conserved in an identical medium. Now that we have defined a lot of geometrical quantity, we can define physical quantities. First, the flux. The flux describes the radiation emitted F by a source, in watt or equivalent units. This quantity gives no information about the distribution of radiated energy in space. In order to obtain information on the distribution of radiating energy, it is necessary to choose an aperture that collects rays in a given direction. This aperture subtends a solid angle from a point on the source. The amount of flux collected through this solid angle defines the intensity of the source at a given point. The unit is watt per steradian, and the intensity is defined as the ratio between the flux and the solid angle subtended by the aperture. How intense is the source considering a specific point? The answer is given by the measure of the intensity. In the case of these two light bulbs, their flux is the same. However, their intensity differs locally. Intensity just gives information about one point. But how to define the collected flux in the instrument field of view? With radiance. Radiance defines the flux emitted by the apparent surface of a source as seen by an instrument with a given collecting aperture. It means that now it is possible to consider a source in its globality instead of just one point. In other words, the instrument that we use has now a field of view, which was not the case previously. Radiance is defined as the ratio between the flux and the étendue. Its unit is watt per steradian per square meter. Irradiance describes the received flux on a surface in watt per square meter. It is the ratio between the flux and the surface of the collecting area. A useful tool in radiometry is called Bugge's law. It is used to define the irradiance of a point source in the case when the collecting surface is far from the source. First, get the intensity to describe the flux coming inside the aperture. Then, get the irradiance by simple division knowing the collecting surface area. Let's now consider a diffuser which can emit light in an hemisphere. An hemisphere has a solid angle of 2 pi. The projected solid angle is pi in order to get the radiance. We can then define the flux emitted by the diffuser and its radiance by the product of the albedo and the incident flux. The albedo is the fraction of light which is re-emitted by the diffuser. This whole quantity is also equal to how the flux is distributed into space. Since it is emitted in an hemisphere, one can define the emitted flux as the product of the radiance of the diffuser and the projected solid angle, and finally the surface of the diffuser. It is then possible to define this way the radiance of the diffuser dividing by the emitting surface, S. We now want to focus on an interesting law in radiometry called cosinus theta-4 law, useful to understand what is the irradiance of axis. For this, we consider a simple system. With a Lambertian source, meaning same radiance in all directions, a lens with a low aperture, so with no spherical aberration which could increase the étendue, and a sensor with several pixels. We first consider the on-axis étendue in the image space. The pixel on-axis has an area of size A. The product between this area and the solid angle subtended by the aperture from the pixel is given by SAP over d squared, and the product of the solid angle and the area of the pixel gives the étendue on axis, G0. When considering an off-axis pixel, the étendues vary. In order to take this into account, we need to take the angle of incidence of the ray off-axis into account. The surface of the aperture has an obliquity as well as the surface of the pixel. The distance between the two surfaces is not identical. It is given by the hypotenuse of this triangle. Solving for x, we finally get the new geometrical extent of axis as well as the irradiance of axis. We observe that the difference between the on-axis irradiance E0 and E1 of axis is a factor cosinus theta-4. So thank you. See you next time.